Hello dear students, welcome to Experimental Techniques in Material Characterization, lecture number 11. I'm Dr. Ph.D. In this lecture, again, we will continue our discussion in part 3 on energy dispersive spectroscopy. Today's topic is signal processing. That is, in this lecture, we will discuss that how the signal that are being processed toward the formation of the spectrum and the EDS analysis. So let's proceed towards today's lecture about the signal processing. So just like we mentioned about the EDX detector, so here you can see the different part of the EDS detectors. Just like we mentioned that the main part of the detector is the portion, the crystals, that is the silicon lithium crystal. So just because of that, it's been called as silicon lithium detector. So silicon lithium detector has no internal gain for calcium K alpha photon with approximately 1000 electron hole pair. So the charge is only approximately 10 raised to power minus 16 coulomb. That is extremely weak. So what actually we need? We need low noise, high gain amplifications. So best multi-stage with a preamp field effect transistors that are immediately adjacent to the detector crystal. So here you can see that. I mean, we have an immediate and adjacent feed, that is field effect transistor to the silicon lithium crystals. So that is, I mean, for the purpose that as soon as we get the signal, it may be amplified and processed forward for the spectrum formations. So the detector, which you can see here, the detectors and the field effect transistors are cooled to about 100 Kelvin, and the cooling is done with the help of the liquid nitrogen devar, which you can see here. And the purpose is to prevent noise and to prevent diffusion of lithium and the detector. So more signal gain provided then by the main amplifier, that is signal now boosted to 1 to 10 volt, where also we have an RC, that is a resistive capacitor circuit, that are being used to shape the pulse to maximize the signal to noise ratio and minimize pulse overlap at the high count rates. So then we have the EDC. Here you can see it's the EDC. So what is the purpose of the EDC? You know what is meant by ADC. ADC means analog to digital converter. The ADC output data to the screen as a spectrum display. So here you can see that that is you see the process. We get the signal from the sample holder with the help of silicon lithium detector. Then we have preamplifier, and as a preamplifier we have field effect transistor, and then after that we have the cooling process. For that liquid nitrogen is being utilized. So onward you can see that we have man amplifier, and that man amplifier and then connected with the analog to digital converters, that is ADC, and ADC then connected to the computer for the final images. So electronic multiplication of signal intensity, is also being utilized here in the process. Uh, Now you have the first signal and ADS detector. So for that you can see the circuit, the circuit here. So what actually happened in this main circuit? So the set of electrons hole pairs are produced by the input of the X-ray. Here you can see that we have the input of the X-ray. So the set of the electron hole produced by the impact of the X-ray on the silicon lithium detector produce a tiny charge. How much 10 is that? That is 10 raised to power minus 16 coulomb. Very quickly, that is in a short interval of time, that is approximately equal to 150 times 10 raised to power minus 9 seconds. So that is the charge, the smallest charge, and that has been processed with the smallest interval of time. That's also mentioned. So the field effect transistor, which act as a free amplifier, changes the charge, uh, that is the capacitance, and to a tiny voltage, that is normally in the millivolt. Here you can see it here. So the output of the feed uh, is shown below at a point B. Here you can see that this is the output of the feed, uh, where the x-axis is the time. I mean, here you can see that the x-axis is the time, and this figure B, and the y-axis is the voltage. I mean, here is the voltage, and along the x-axis we have the time. So the jump represent, here you can see, I mean, we have a jump. So this jump represent the presence of voltage proportional to the number of the electron hole pair generated by each X-rays. So protons 2s jump is of higher energy than the proton 1s jump, which is higher than the proton 3s jump. So at a certain point, the field reaches the limit of the number of charges it can hold, and then there is a reset of zeroing back to some baseline where it start over. So this is the characteristic of field effect transistor, and the people who have the knowledge of electronics, so they don't know that what actually happened. So following this are electronic to shape the voltage and to a pulse that can be counted. So along with that, we have processing time and pulse pile up rejection. So what it means? I mean, with the single formations, we have so many things. So one of the key thing is processing time and pulse pile up rejection. So here you can see we have these two figure. Here you can see the signal processing. So we have a process, the signal process being plotted. Against the voltage. Here along the y-axis you see the voltage, and along the x-axis you see the time intervals. And here you have the setup for the signal. So the user can tweak the time constants, that in short we call the TC, which set the time allocated and the electronic to process each pulse, that is along the x. Each pulse means the X-rays. So here in this figure, a short TC, that is time constant, which is equal to 1 microsecond. So the short time constant permit each pulse to be counted correctly. So here you can see that we have pulse 1 and this is pulse 2. So the short time intervals, it enables each pulse to be counted. But if we increase the time, so at longer TC, that is almost 10 microsecond, it means the gate is often longer, and a second pulse, which you can see it here, can enter and be incorrectly added. So what is the result of that? This pile up and causes distorted spectra. So here, the time interval, this is the effect of the time interval, the time constant. Increase from 1 microsecond to 10 microsecond. So that what exactly happened here. Therefore, the circuit, we added the circuit 4 here. Here you can see we add circuit 4 here in the basic circuit that you people have seen on the previous slide. So here we add, the circuit. This additional circuit is added. So what is the purpose of this circuit? Circuit number 4. So its purpose is it's acting as a discriminator. It's act as a discriminator, and just because of that, you can see it here that how the image they are being discriminated from each other. So this is added to sense when pile up occur and to ignore that pulse. So the circuit number 4, that is the discriminators. It's adjusted here, and its purpose is to to sense when pileup occur and to ignore that pulse. And we have also the concept of the dead time. So what is mean by the dead time? So dead time is the period during which the detector is busy and cannot accept or process the pulses. So this can introduce error unless it is accounted for either by extended counting time or correcting for it and the software. So in most systems, the user set the live time, which is the time during which counts are actually counted, and the real time is automatically determined by the electronics or software. So dead time. Optimal dead time is in the range of 30 to 35%. This optimizes both user and machine time and moderate to the high throughput of the count. Detector performance, that is peak resolution, that how we resolve the peak. So the characteristic X-ray generated and the specimens are very close to the line. That is only a few electron volt wide at most. However, the conversion of X-ray to a pulse and the detector has several variables, that is mean imperfections, that broaden the peak to between maybe 135 to 200 electron volt, depending upon the type of the detector and how well maintained it is. So the narrowest of the peak is measured by the width of the peak at one half of the maximum intensity of the peak, and that is called what that is called FWHM, which means full width half maxima. So an ADX detector, it is usually measured at the manganese K alpha position with a value of 160 electron volt and below. So modern type of the detector, that is which mostly come after 2005. One are quoted at smaller than 130 electron volt. So why manganese? Why manganese K alpha for ADS resolution? So we remember the ADS companies or their engineer mainly do not want to have to carry around an SEM or EMP to be able to test, repair, and calibrate an EDS system. So instead, they carry a small 1 diameter into 2 long tube that fit over the end of the EDS snout. So inside it is an iron 55 isotope source, which has a half-life 2.7 years, which emit an intense X-ray at 5.985 kilo electron volt. So which is only a few electron volt different than the manganese K alpha. So that is the key reason that why manganese K alpha for ADX resolutions. That's been clarified now. So that's all we have for this lecture. I hope you learn a lot. But stay tuned for the next lecture, because in next lecture we will have a discussion on spectral processing and EDX analysis. So that will be part number 4 of the lectures on energy dispersive spectroscopy. So stay tuned with the next lecture. Till then, bye bye.